Like the base of the shape is an equilateral triangle where the side is equal to x and the height is equal to 8.
Oh.
And then it gave you a solution and it was like find the area or something like that. Or the volume. It gives you the volume and then it says find the area and I was like,
it was surface.
Yeah.
It was one of those shapes where it's the surface
I tried
area.
to draw it and I was like,
I didn't know where they got the square roots from. Because I squared it of 3 over 2, I was like,
Oh.
because I was thinking an equilateral
Because
triangle
it's
is
a
like
triangle.
30, 30,
Equilateral
30,
triangle
60, 60 or
doesn't
something.
have
It's like
60,
45.
30, Annie, so that means
Yeah, 30, 69.
if
Yeah.
this is x, then
Couldn't do it.
Was there a solve for X one with the trig?
see, I didn't know
It's
that. I didn't know
Yeah,
that.
I think
I
so.
don't know.
But I
the
did
things
that
that
one
over
where I
really
got
helpful,
to
like,
make
I was
you math
like,
it all,
all
but
the
I
time.
didn't match their answer.
Yeah.
And I had to
I felt
match
very
their answer. I was
It wasn't bad. It wasn't bad.
I'm glad to hear that. Usually they come out here going, you've not taught us any of this.
I was surprised.
No, I did pretty well. I was like, at first when we did the take-home test you gave us, I'm like, oh, I'm not gonna do good on the actual test. This is so much easier than the actual one you gave us.
Wow.
blanked
Okay.
on the
Well,
back.
It was easy. I was like,
Maybe everyone failed last year, so they're like, let's try and make it a little.
yeah, maybe. Last year was tough. So what I probably could have you guys do is, obviously we don't do a semester exam in here, but normally I do a survey, which is kind of like, and I'll tell you more as we get closer. You know, what topics did you feel like I did okay, like teaching and keep doing it the way I'm doing it? What topics could I do better at? And perhaps, you know, what did I do that wasn't quite teacher worthy, you know, in that aspect. And then I usually say, I have a couple things. It's just, and I'm not asking you to write a book. I'm just kind of asking you to say, because I was told you didn't really help us learn how to solve for x's very well with trigonometric identities 2 years ago. And so that was something I really focused on because I feel like I really hit the ball out of park with this one. You knew where the quadrants were, you knew how to pick the next one, you knew how to get there. In the past they would not. So I felt like I did a better job, and that was because kids told me you got to do something different there. And so to me, you know, teaching is still a learning process every day. What can I do to make it easier for you guys to go in there and come back and say, it wasn't as bad as I thought it would be? That makes my heart smile. So, yes.
But in the future, your other classes are also going to have those videos. I'm not going to delete
You're
them.
not going to delete them?
No.
Oh, I love that. Okay, well, hopefully that's true. And this year I might have been really the best teacher of my all time. So I can slack next year then, right?
You can just say, go on YouTube.
Okay.
Yeah, I don't feel like teaching.
Sorry, you better watch last year's version. Excuse the outfit.
I did like this year. Like, I felt very confident in this. Like,
I have never had a group of kids come back and say I felt confident. I've never had
I
that.
feel like I was as prepared as I could be.
Okay.
Because there was no way I was gonna know all this stuff
before
that
the review.
I got like
Right.
50s on the test for.
I
but-
understand that. But honestly, you're not going to go in. Are they expecting you to go in and get a perfect score? No, they wouldn't create a test that you can get a perfect score on, I promise. You know, so the idea is, you know, you had a comfort level with it, and were you able to attack it? So that's where we're at. Anyway, this is the last chapter of the year. It's about the normal distribution curve. Okay, you're going to need your bright colored sheet of paper that has statistics on it. And I think that I've done a good job getting you ready to know what that formula sheet looks like. We've utilized it. You're comfortable with it? No?
No. I accidentally drew my unit circle on my formula sheet.
Right. You're not going to use a unit circle next time, and we'll throw that formula sheet away.
Okay, so there's like, they're not gonna like care that I.
No, we'll throw it away, unfortunately. We have a few extras from last year that we were able to bring through.
Carlos borrowed my statistic formula sheet.
Carlos Penrod, you'll never see it again.
He asked for the test, and like, yeah, I guess you can borrow it.
Oh, okay. You're going to need it for this, so unfortunately. Is there other people out there that don't have it?
Don't have what?
The formula sheet for statistics.
Yeah, I do.
Yeah,
Yeah.
you
It was
need it.
honestly so weird to me looking at it on white paper.
I know.
Yeah.
So I shouldn't do it bright color? Oh, okay.
It's easy
They
to
had it all
find.
divided out. It was cute.
Yeah, it's actually, I photocopied that into the bright color sheet paper. So actually somebody goes, the area of the circular sector is not on there, and I'm like, I can't help you, buddy.
It is.
It's on there.
It's like 1/2 r
Square theta.
Yeah.
So I was like, ah. Anyway.
I definitely was trying to figure out what was what.
Well, no, I actually attempted it.
Okay, so this is my last lesson of the year. Really pay attention. This is, no, this kind of pulls together both. Yeah. So this is it. This is the last lesson of the year. It kind of pulls it all together. My goal for you is to, I'll figure out we're going to test it, because, we're getting to it where we may not be together much, so I'll figure that out. But as of right now, okay, so what we're going to be using here is called the normal distribution, normal bell curve. Okay, have you seen it before?
Yeah.
Oh, we've referenced it before. Actually, I have in this class as well. Talking about it, like for example, on a test. If I'm looking at a normal bell curve, and this is my testing, like grades from a test, what this tells me is that a lot of people did pretty well, right in the center here, okay? Few people didn't do well, and few people did really well, okay? So what this centers around is the mean. So the normal bell curve, 95% of the time, will work around your mean. So you're very center of this. There are skews, like a skewed right and a skewed left, where it would look more like straight line, big hump here, meaning everybody got A's, or straight line, little big hump here, meaning everybody failed. We don't want that, okay? As a teacher, you kind of really look at that, and you say, what does my normal bell curve look like? I want to make sure that I'm on target and that my kids are actually learning what they need to learn. Okay, I want to use the same numbers that so when I'm talking about this normal bell curve, what typically, let's say that we're talking about the heights of kids in a class, okay? And if I tell you that the mean is 180 centimeters, we'll measure them in centimeters because that's what you'll see on a test, okay? The way that they represent the mean is not by the word mean, it's by this symbol here. It's called
mu.
Okay? So mu is what we represent the mean with now, in this particular case. So mu, the mean, will normally fall right down the middle. And in this case right here, we're going to call it 180 centimeters. Now, what happens to the left and the right of it, we're going to create three equidistant lines. I got excited and went too fast here. We're going to create three equidistant lines, and those are what we call standard deviation. Okay? So these are each known as a standard deviation. So let's say my mean is here, and I have a measurement here. It would be one standard deviation away from my mean. Over here would be 2 standard deviations away from my mean, okay, etc. And then 3 standard deviations away from my mean. Everybody cool with that? What about here?
-1.
Yeah, -1. It would be 1 away, but in the negative direction, so it would be below the mean. Here would be -2 and -3. Okay, is everybody cool with that? Between -3 and +3, you actually get 99.8% of your scores will fall into that range. Okay? So from -3 standard deviations to +3 standard deviations, 99.8% of those test scores or whatever we're measuring, or heights of people or whatever we're measuring, will fall in that category, yes.
So 0.01% and 0.01% are past that line.
Correct. Then they're equidistant either way, okay? So Is everybody cool with that so far? So if I know that something is within 3 to -3 standard deviations, I know pretty much the whole kit and caboodle falls in there, right? Now, from here and here, okay, so from 2 standard deviations to 2 standard deviations, 95% will fall in that category. Okay. So everybody good so far? Does anybody know what the middle category will be? Not quite. It's actually 68. So it's 34 each way. So from here, I'm going to try to make it where it looks just like the rest of it here. From here to here, 68% will fall. And does that make sense that if I'm looking at test scores and 68% of them fall 1 standard deviation left or right of the mean, that the average score is pretty good if the mean was a good score in the first place. You know, if the mean score is an 80, then I know 68% will fall from the left to the right of 80. 1 standard deviation, whatever that standard deviation is referenced as, and I'll explain how that works. So does that make sense that when you're looking at this, you're looking at pretty much the whole set of data that you're going to be referencing, okay? Everybody good so far? Okay, so let's say I have runners in a marathon. Okay, so runners in a marathon, and we're going to say that the amount of hours it takes to run a marathon, which I'm not even sure if this makes sense, but let's say my mean is about 3.8. Is that, any runners, tell me if that's realistic?
Hours?
Yeah, 3.8 hours for a marathon. What kind of marathon would I run? Half one or a full one?
Troy can run 10 miles in like less than an hour, so then.
But is Troy in the mean? Is Troy on the end, or is Troy kind of like right down the middle of the pack?
Or ahead of the pack.
He'd be ahead of the pack. So I think 3.8 hours might be a half marathon then. I don't know. Is it 20? How many miles is it a marathon? First of all, 26. Okay. Okay. So anyway, this is like data that I pulled off.
It's a special marathon.
It's a special marathon. Yeah. We're running in place. Okay, so that would be my kind. I'd have to sit for a while. Okay, so let me say, I did it in a wheelchair. So we have 3.8 hours is my mean, okay? And I'm going to tell you that the standard deviation, okay, and the way that I represent standard deviation is this symbol right here. It's called sigma, okay? Sigma, standard deviation, I'm going to tell you is 0.5 hours. What does that mean? Half hour. Everybody cool so far? Okay, so if I was 1 standard deviation away from 3.8, what would that be as far as the amount of time? It would be 4.3, right? Okay.
You just multiply that by 0.5?
I didn't multiply it,
Or-
what I do?
Or you
I
add
added it, right?
Yeah.
How about to the negative 1? What would that be?
Minus 0.5.
Minus.
3.3.
Okay, let's go 2 standard deviations. What do I get?
4.8.
4.8. Okay, and negative 2 standard deviations? 2.8. And last but not least, 3 and negative 3. Do you agree 5.3 here?
Yeah, 5.3.
And 2.3 here? Is everybody cool with this? So let's talk about numbers as we had them up here. Do you agree that 99.8% of my runners finish the race between 2.3 hours and 5.3 hours? Okay? And I do understand that bigger's not better here. You want to get here, right?
Yeah.
Am I right? Yeah, yeah.
So is that going to be like the case every time, like 99.8% of everything is going to be within?
Always will fall between those and those, right? Yes. Okay. So far, so good? Yes? Okay, so this is represented as a normal with a mean of 3.8, and we put variance here. So what is variance in accordance to, what's variance?
Squared, standard deviation.
It is. Can we remember that? Right? It's the squared of the standard deviation. So what's the standard deviation here? 0.5. So what's the squared of it?
2.5.
0.25, right? 0.25. So if they give you something and say x is a normal, what's the other kind we did before? You guys remember? That kind of looked like this when we wrote it. Binomial. Remember, binomial had right, and B had to be there, but it also had only two options that could happen. It was like a success or a failure, right? So those are the kind of things that we had to look at for binomial. Why do we not have a binomial here? Because I could end in 2.3, I could end, there's multiple things that are happening here. Okay, so the way we write this is x is a normal, and the mean goes first, and the variance goes next, which is the, if I was to write it here, squared is the variance. Okay, so far so good? Now, that's all fun. Well, at least I think it's all fun. So here's the deal. Here's the deal. When we're working with these, we are not going to be working when you have your variance and your mean to be random numbers. We're going to be working with something called the standard normal. Okay, so the standard normal distribution. That is a random one. We're talking about a marathon, whatever you have. Bless you. This is what we're going to refer to as our standard normal, where our mean is 0. Then if I was to go 1, 2, 3, -1, -2, -3, to the right and to the left standard deviation purposes, I would say this would be 1 standard deviation away from the mean.
Mm-hmm.
This would be
2.
2 standard deviations away from the mean. This would be 3. And vice versa. -1, -2, -3. This is what we refer to as the Z, rather than our normal. It's a standard normal. It's represented by what we refer to as the Z. Okay? And the way that it's written out is that Z is a normal with 0 and 1. So how did that change? Okay? What happened here is we went from an exact on our whatever our story is, we went from exact of a 3.8 as our mean to a random would be. So what would be my 0 in that case would have been a 3.8. That would have been my mean. It's not always going to be 3.8, so we have to change it around sometimes. So why do I need to go into a Z form? If you look at your bright colored sheet of paper, okay, what you have is what we call a normal distribution table. Okay, and what this is it's all in terms of Z rather than a regular normal distribution. So what we have to do is we have to take information that's given to us as a normal, we have to convert it to a Z, and then we can utilize it. Okay, so that's kind of like in a nutshell what we're going to be doing with this. So I have my Z table. I'm going to let you draw this one out, and right below it I'm going to have you mirror the same one. Hopefully it looks just like it. So not fair, but you guys get the idea. It should be like equal size, equidistant, whatever, of the one above it. Okay? And the way that I convert, okay, I always know that my center of the Z is going to be 0.
Mm-hmm.
It's always going to be 0. Okay. The way that I convert is this formula right here. Now, I don't know whether this is on your bright colored sheet of paper or not. How I convert from a regular, normal distribution curve to a Z distribution curve is by this formula right here. And what this formula is these are my X values, my observed values for my story, whatever that is. I'm having a group of people running in a marathon. 3.8 hours is the mean of that group of people. That's my story, okay? So these are my X values. My mean is the very center. And what is this sigma again? The standard deviation. Okay, so far so good? So what we're going to do is we're going to take this and we're going to convert it. And we're going to see how this works. I want to convert the 4.8 and see where that lies on my Z table. Okay? So I'm going to take Z is equal to, my X is my observed value, 4.8. My mean is 3.8. I'm going to divide it by sigma, which I told you was 0.5. And when I do that math magic, I get 1, yes?
Are they always going to tell us that?
No. We're going to actually go from Z to normal and normal to Z. So, yes.
What's the point of them having all these, like this table?
Give me 5 more seconds and well, 10 more seconds. Give me a few and I'll get you there. So what do you get when you get this? 1 divided by 0.5, what's that answer? 2. So that's saying from here, it's 2. Okay, cool.
In Z-score format.
Ah. Let's go ahead and do, what's that?
That makes sense.
It should make sense, right? Let's do 4.3 and see what we should get. What should we get? We should get
1.
We should get 1, right?
Oh.
Let's see. Yeah. So it's going to be Z is equal to 4.3 minus 3.8 divided by 0.5. And what do we get? 0.5 divided by 0.5. Indeed, it's 1. Okay? Does that make sense? Without doing the math, what should 2.8 turn out to be?
Negative 2.
It should be, right? So let's make sure. I've got my observed value, 2.8, minus 3.8, divided by 0.5, and its Z equivalence is negative 1 divided by 0.5, which is indeed negative 2. Does that make sense? So every single normal curve has an equivalent Z curve to it. So far, so good? So each of these, I can just kind of fill in the blanks, each of these have their equivalent scores that kind of mirror up to them. Is everybody good?
How come you can't just see that on that chart that it's 2 standard deviation away?
You can.
But you need to know the formula?
Right.
Because when you do things that vary in between. there's
Right.
deviation.
You're going to need to figure out, like you could have 1.1, you know, that sort of thing. All right, so are we good so far? All right. The next thing we're going to do, and this is where the fun stuff comes into play. The next thing we're going to do is we're going to figure out how that table comes into play. What the table does for us, number 1, it's always in Z-scores. Number 2, it gives us probabilities. What is the probability that I finished the race in less than 4.8 hours? What is the probability that I didn't, I finished the race in less than 2.3 hours? There's a myriad of different things that we could do with this, right? So first and foremost, I have to convert it to Z-scores. Then from there, I can do my probabilities. Now, does everybody have a bright color sheet of paper?
Mm-hmm.
I do
No.
not.
Let me put it up on the overhead. I don't know if I have the.
Like from the negative 3 to the third is always going to be 99.8%.
Yeah.
So if you didn't have this chart and you were trying to figure out
No.
the probability of going to like the second Z-score pass, you couldn't do like 99.8 minus 95 divided by 2 and then subtract that from 99.8.
Okay, that, yes and no. But, because what happens is, you're not always going to be perfectly 2
Okay.
or 3. You're going to be like at 2.1 or 2.25. You know what I'm saying? So in the perfect world, we are always on the perfect z standard deviation, but it's not always there. Okay, so let's do this. I'm going to show the problem, and then hopefully you guys can kind of share your wealth around here. I wish I had extras. So here's what's going to happen. A z table, that table you have in front of you, at the very top of the table, can somebody in words describe what you see? This guy right here. What is that? What do you see when you look at that? You see a line. Does it go all the way to 3? Bone. You see a line, right? It looks like this, and then this whole thing is colored in, right? So if you look at it, that's what you're seeing. Now here's what's happening. When I ask you for a percent, the only thing that this measures, this graphing thing, is anything to the right. Okay, anything to the right, and it has to be to the right of the actual mean, but anything less than that. So let me explain what that means. If I ask for a probability of something being less than, let's say here, I know that I'm looking at this whole grouping of numbers. So the question that I ask you is, do you guys agree that this whole thing is 100%, right? And where does 3 lie? So you're going to look on your little table, and you're going to look for the number 3. Okay? So good luck with the 3, right? So you're going to look at the number 3, and it's 0.30. Really is what. Oh, go back down. Sorry, 3. Doesn't it give you 3?
No, it ends in 2.9.
No. Go down to the bottom. The very bottom. Here's how this works. This is a really funky chart. I don't like the one they're giving you. Here's how this works. See the Z at the very top? Scroll your eyes across to the number 3. Okay? And you're actually looking for the 3.0 of it. So Z is 3.0. I don't like that at all. Holy cow. Let's talk about what it is. If I know that this is 3, right, and I know that this is everything before it, talk to me a little bit about what I know. I know that from here and back, it's actually going to be everything to the left of that is my percentage-wise. Okay? So if I'm looking at this, I know that what is the number that falls at 3? I'm not happy with that chart. And that's not going to help because you guys need to use that one. There's like 20 million different charts that we could potentially use. Ones that go up to 4. Z-score tables. There's one right here. There it is right there. Is everything cool? 3.0. Yeah, 0.987 is the answer. So everything from the left to here is 0.987. Do you see that located on there somewhere?
Let's see.
Mm-mm.
I see 0.9987.
I have 0.987.
Where?
It's it's 0.2, 0.2, and 3.
2.2.
And 3.
2.2 and 3. Yeah.
That's
Like,
all I got.
what's with the 0 through 9 on the top? What is that?
0 to 9 on top. Let me do this one with you. Let's see if we can come back to that. Let's say I gave you, let's go with something that's easier to start with. Talk about this one with me. So I have a normal, this is my mu, which is 0, okay? And I want to know everything to the right of here. tell me what you get.
50.
50%, right? Does that make sense? So my mu is 0 and everything to the left is 50%, yes.
You said to the right.
But you are gonna, that's the deal. It's everything from here forward I can measure back. Does that make sense? So from here I can measure back. I know it's 50% have to fall into that category. Does that make sense? Somewhat? So on your thing, let's see if 0 corresponds to 50% somewhere on there. Right there.
0.5.
So right here at Z is 0, it's 0, and that's how it reads. So do me a favor, look at the top where it says Z, and then look at the decimal below it, like to the right, on that right side, on your left.
Just line it
So
up.
it's 0.00 is 50%. Does that make sense? Okay.
Where's the 0, 1 stuff on the top?
Say it again.
Like is that the standard deviation from 1, 2, 3, like where it's located? That makes sense? Like where it starts? I don't know.
What do you mean?
Like what is the 0, 1, 2,
Yeah,
3?
so here it is.
At the top, you mean?
Yeah. So you have 0.0 is 50%. 0.01.
But if you have 2 and then 2, wouldn't this be 4?
So 2 and 2. It'd be 2.
The right here, see?
Right. Let's do 2.0. Like 2.0 is 0.9772. Does that make sense? What would 1.5 be? 0.9332. Does that make sense? No? Can you see where
I see where
1.5?
it's located, but I don't understand like what. So we're just what do those numbers mean? That's why I don't understand.
Okay, so if I'm looking at one standard deviation away, I'm looking at everything percentage-wise that falls behind here. So along this column, look for the 1.0. Do you see it? And then I'm looking strictly for the 1.0 in the perfect world that we were talking about earlier, Maddie and I. So look for 1.0, and the first column, because it goes 1.0 is here, and then up here it says 0.0 whatever up top, 0 up top. So that means 1.00. So kind of connect those dots, and what do you get right here? in
Oh,
that
that's
spot?
what it means. It just goes past the
Yeah.
decimal. Okay, that makes
Right.
I didn't know what the
Yeah,
numbers
that's the
were.
hundreds.
Right.
That's what I was like. Well, I
Right.
understand. You understand like the
Now it
0.
makes sense?
Now it makes sense.
Okay.
I didn't know those numbers.
So, like, what would 1.0 be? Point what?
84.
84.
So-
38.
0.8413.
0.8413. So 84% fall behind that level. Now, here's the kicker to this. I told you everything has to be measured to the left, right? What happens if I do this? And I want to know, that's a little to the left, let's put it here. I want to know everything that falls this way.
So you can
100
subtract
minus
subtract
that.
it from 100?
Right. Or you do 1 minus this.
Yeah.
1 minus 0.8413. Exactly right. Does that make sense?
Now it makes sense.
Okay, so what percent would fall in that end of the tail? Whatever 1 minus that is.
1.5.
Okay? How about this? What if it was, so there's my mu.
Do you find it for a regular one and then subtract it from 1?
You always find it for the regular one and then subtract it from 1 because they mirror image each other. So what is true for this amount would be the same truth for this amount. Does that make sense?
So you have to find,
You'd have to find the stuff to the right of it. You would find, first of all, you'd find this, subtract it from 1 whole,
take that number.
and then take that number, and that would be the same answer up here. Yes?
So when you read these tables, you would start with this and then you
Yes.
add that.
Yes.
So where it says 2.9, it would be 2.90, 2.91,
Correct.
all the way to 2.99.
Correct.
Why does it stop at 2.99?
Well, so then what happens is you add that number to the end of it. I'll show you how to add that part when we get to one of those. But let's go ahead and do another one and see if you can find it on there. Now, you're going to come across a million different z-score tables, which is kind of a bummer because they They're all different with the way it looks, but, okay, so I wanna know the probability that z is less than 1.5, okay? So that's basically how it's gonna be written. So I know mu is here, I know 1 is here, I know 2 is here. So that's not a straight line, but you got the idea. So I wanna know the probability that it's less than 1.5. So it's all this stuff back here, correct? So what is the probability it's less than 1.5? Well, that's a straight shot. You look on your little chart, and that's a straight answer. 0.9332. Okay, so everybody see that?
Yeah.
So that's like 92%.
Correct. Does that make sense? Yes.
What are the decimal numbers on the left? On the left column.
The decimal numbers on the left column.
Like
You mean
the
like-
Z.
You mean like 1.5?
No, like 0.0, 0.1, 0.2,
That's the
0.3.
standard deviations
Oh,
of the
okay.
z-score.
Yeah. Okay, so are we there? Now, what if the question says, I want the probability that z is greater than 1.5? Okay? I want z is bigger than 1.5.
So yeah, it'd be 1 minus that, and you're gonna be left with that.
Yeah. So really, I know that I'm talking about this section here. You guys agree? But I can't just find this section. I have to find it in relation to the left. So I would find this right here and subtract it from 1 whole. Yeah, 0.0668.
Miss K?
Yes, hon?
So when you're doing this, you're only finding the stuff to the left of it. There's no way for you to find that right. The only thing that you'd have to do is find the left and subtract it from 1 whole to get the right.
Right, correct. And your line that you have to reference and use every time has to be to the right of mu.
Okay.
You can't just find it over here. You have to start here and work your way back.
And it can't be on mu?
Yes, on mu would be 0.5.
Mhm.
Okay, what about this one here? I want, P is, Z is greater than, negative 1.5.
So, 1.5 on this side, so we have to go back and do it that way.
Well, because what it is, let's talk about what it looks like. So technically, Z bigger than negative 1.5 looks like what? It's over here, and that's 1, and that's 2, so it's like here, and it's
The rest of it
to the right of it, right?
Yeah.
mirror imaged.
Wait,
Go ahead, yeah? So it's a mirror image of which one?
The
The
first,
1.5.
the first one.
The first one, which means, it means this would be the mirror image of it. Would you agree?
It's the same
Like,
thing.
This is the same as that, right? So the answer would be what?
0.9332.
Yes.
Would you have to, you don't do like negatives, if it's like the same, it's still gonna be a positive number no matter which
Because
side
it's a
you go.
percentage.
Well, what they do, and when they're teaching it, is they say the fact that z is bigger than that is going to be equivalent to z is less than that. Does that make sense?
Yeah.
Okay. So yes, you got 0.9332.
And what were you finding when you did that part, the 1 minus 1?
Here?
Yeah.
I want, at 1.5, the stuff bigger than it, greater than
Okay.
it. Does that make sense? So that tail. Now, how about this one? P is less than negative 1.5.
It would be 0.068.
It would be the same as this tail here. Does that make sense? Because they mirror image each other. All right, are we comfortable with that? We're getting, okay? All right, so let's do this problem here. Now, we can kind of, what's that? I don't know. What time is it?
It's 17.
Wait 2 minutes.
Shoot, we'll have to finish it tomorrow. Okay, so do me a favor and make sure you have your worksheet with you tomorrow. Please try to find your Z-score table. This is the only
Just
thing.
print out one since Carlos has one too, both
Yeah.
mine.
I should try to print out more, you mean?
I don't print out, I just need it, so I'll print one out.
Yeah, I can print out a lot.